Drag your fingernail across the back of your hand. Do it slowly. Feel that faint sting. See the pale line that rises for a moment before your skin quietly repairs it? Here on Earth, that scratch is meaningless. It disappears before it earns a memory. Now picture the exact same scratch, same fingernail, same shallow depth, same tiny, almost laughable mark. But this time it happens on the outermost layer of a spacesuit 200 miles above your head, in orbit. That scratch kills you, not eventually, not hypothetically, in roughly 90 seconds. And I want to walk you through precisely why. Because the physics behind that statement is both exquisitely elegant and deeply terrifying. It hinges on something you have never consciously thought about, even though it has been pressing on every square inch of your body since the instant you were born. Let's begin with something simple, almost insultingly simple. A pot of water on your stove. You set it on the burner, turn the knob, wait, eventually the water boils. Everyone knows the number, 212 degrees Fahrenheit, or 100 degrees Celsius if you prefer. But pause for a second. Why 212 degrees? What is magical about that temperature? There's nothing magical about it at all. Inside that pot, water molecules are in constant motion, jostling, colliding, vibrating. The warmer they get, the faster they move. Some near the surface are especially energetic. They want to escape into the air as vapor, but something presses down on them. The atmosphere. Above that pot is a column of air stretching miles upward to the edge of space. That column has weight. It presses down with about 14.7 pounds per square inch. We call that 1 atmosphere. That pressure tells the molecules, stay. Boiling happens when the water molecules gain enough energy to overcome that downward push. When the vapor pressure of the liquid equals the atmospheric pressure above it, the molecules win the tug of war. They escape. That's boiling. There is no sacred temperature in the universe. There is only balance between pressure and molecular energy. Change the pressure, and you change the boiling point. Go to Denver, about a mile above sea level, and water boils around 202 degrees Fahrenheit instead of 212 degrees. Less air overhead, less weight. The molecules don't have to fight as hard. Climb Mount Everest at nearly 30,000 feet, and water boils at roughly 158 degrees Fahrenheit. You can make tea there, but it won't be very good. The water simply isn't hot enough to extract the flavor properly. At the top of Kilimanjaro, around 160 degrees Fahrenheit, in a laboratory vacuum chamber, you can make water boil at room temperature. No heating at all, just remove the air. I've done it. A flask sits on the bench, cool to the touch, and once the pump lowers the pressure enough, the water begins bubbling vigorously. It looks like sorcery, but it isn't. Lower pressure, lower boiling point. Freeze-drying food uses the same principle. Lower the pressure in the chamber, and water leaves the food at low temperature. At high altitude, your tongue dries faster, not because you're necessarily dehydrated, but because moisture evaporates more readily when less air presses down. Your body is already engaged in this pressure battle constantly, whether you notice or not. Now take the idea to its logical conclusion. There exists a boundary in the sky where atmospheric pressure becomes so low that water boils at 98.6 degrees Fahrenheit, 37 degrees Celsius. That number should sound familiar. It's your internal body temperature. That boundary lies at roughly 63,000 feet, about 12 miles above Earth. It's called the Armstrong limit, named after U.S. Air Force physician Harry George Armstrong, who recognized what this altitude implied. Above the Armstrong limit, exposed body fluids begin to boil, not because they're hot, because there isn't enough pressure to keep them liquid. When people hear boil, they imagine heat, a screaming kettle. That's not what this is. Your body temperature stays the same. The air simply stops holding your fluids together. Saliva on your tongue begins to bubble. Moisture in your eyes starts to fizz. The thin liquid lining the alveoli in your lungs, the tiny air sacs responsible for oxygen exchange, begins turning to vapor. In 1966, Jim LeBlanc, an aerospace engineer at NASA's Johnson Space Center in Houston, experienced this directly. He was inside a massive vacuum chamber testing a prototype spacesuit. The air hose feeding his suit accidentally disconnected. The pressure inside his suit dropped almost instantly. The last sensation he remembered before losing consciousness was the saliva on his tongue beginning to bubble at normal body temperature. Technicians repressurized the chamber in about 30 seconds. LeBlanc regained consciousness. he survived without permanent harm. But consider the timing. He lost consciousness after about 14 seconds. Had repressurization taken 2 minutes instead of 30 seconds, his name would be a fatality entry in an archive. Now move beyond 63,000 feet. Space isn't thin air. It's essentially no air. In low Earth orbit, the external pressure is about 1/1,000,000,000th of sea level pressure, functionally zero. No air to breathe, no air to conduct heat, no air to carry sound, no ozone layer blocking ultraviolet radiation. Though in low orbit, Earth's magnetic field still provides partial shielding, the environment is otherwise the closest thing to total emptiness nature offers. And it's only 200 miles up. That vertical distance is less than a road trip from New York to Washington, yet straight up, it takes you from the most life-friendly environment in the known universe to one that kills you in seconds. Between an astronaut and that void stands a spacesuit. About 13 layers. That's it. Roughly 13. Layers of specialized materials, together weighing around 110 pounds on Earth, forming the only barrier between a human being and rapid death. The innermost layer is a cooling garment, essentially long underwear threaded with plastic tubes circulating chilled water. In vacuum, there is no convection. Heat doesn't drift away. Without active cooling, an astronaut would overheat inside the insulated suit. Above that sits the pressure bladder, urethane-coated nylon, airtight holding pure oxygen at about 4.3 pounds per square inch. That's far less than 14.7 psi at sea level, but it's sufficient to keep fluids liquid and lungs functional. Surrounding the bladder is a restraint layer of Dacron, preventing the pressurized bladder from ballooning outward like an overinflated glove. Then comes the thermal micrometeoroid garment, multiple layers of aluminized mylar separated by spacer fabrics, topped with a tough outer ortho fabric made from a blend including Gore-Tex, Kevlar, and Nomex. In sunlight, external temperatures in orbit can reach about 250 degrees Fahrenheit. In shadow, they can plunge to minus 250 degrees Fahrenheit. These swings occur every 90 minutes as a spacecraft circles Earth. The reflective mylar layers limit thermal extremes. But thermal protection isn't the only threat. Micrometeoroids, tiny particles of rock and metal, zip through orbit at 8 to 16 kilometers per second. 16 kilometers per second is about 36,000 miles per hour. A rifle bullet might travel 2,000 miles per hour. These particles move roughly 18 times faster. At those velocities, a grain of sand doesn't simply punch a hole. The impact energy vaporizes both projectile and target, creating plasma and shock waves. Layers of the suit are engineered to fragment and disperse that energy before it reaches the pressure bladder. And most of the time they succeed. But orbital debris adds to the hazard. Flecks of paint, fragments of old satellites, bits of rocket stages. In 1983, a tiny fleck of paint struck the Space Shuttle Challenger's windshield hard enough to require replacement. In orbit, even trash is lethal. If a particle penetrates the protective layers and punctures the pressure bladder, oxygen leaks into vacuum. The suit deflates, not explosively, but steadily. Pressure drops. The body begins the process LeBlanc experienced. Blood does not instantly boil. It remains within pressurized vessels. But exposed fluids, saliva, tears, lung moisture, vaporize. Dissolved nitrogen forms bubbles in tissues, similar to decompression sickness and diverse, but far more extreme. The body swells to perhaps twice normal volume. Skin holds, but tissues distend. You retain useful consciousness for about 15 seconds. After that, unconsciousness. The heart may beat for another minute or two. If pressure is not restored within roughly 90 seconds, oxygen deprivation causes irreversible brain damage. This process is called ebullism. Holding your breath makes it worse. Air trapped in lungs expands violently in vacuum, potentially rupturing lung tissue. The correct action is counterintuitive. Exhale continuously, just as divers doing rapid ascent. Temperature extremes are secondary. Vacuum kills faster than cold or heat, so return to the scratch. If it damages only the outer ortho fabric, no problem. If it penetrates to the pressure bladder, you have a leak. During STS-37 in April 1991, astronaut J. Apt's glove bladder was punctured by a stainless steel palm restraint bar during a spacewalk. The hole went unnoticed. His hand and the inner glove partially sealed it, preventing significant depressurization. Millimeters made the difference between a routine EVA and catastrophe. After such incidents, astronauts began inspecting gloves periodically during spacewalks. Gloves are thinner for dexterity, and thus more vulnerable. The weakest point is also the most frequently used. Engineering failures often occur at interfaces, joints, seams, flexible boundaries. The 1986 Challenger disaster illustrates this. The shuttle failed at a joint between solid rocket booster segments, sealed by rubber O-rings. On a 32 degrees Fahrenheit January morning, the O-rings lost resilience. Hot gases burned through. 73 seconds after launch, the vehicle disintegrated. 7 lives were lost because a quarter-inch ring did not seal properly. Margins are thin in engineering. They are thinner in space. The International Space Station travels about 17,500 miles per hour. A micrometeoroid approaching from the opposite direction might yield closing velocities near 40,000 miles per hour. The energy of a sand grain at that speed can rival that of a bowling ball thrown at 60 miles per hour, concentrated on a microscopic area. Risk is never zero. Air does more than we realize. It carries sound. In vacuum, a tearing suit makes no audible warning. It distributes heat. It filters ultraviolet radiation. It shields against high-energy particles. On Earth, the atmosphere provides radiation shielding roughly equivalent to 10 feet of water overhead. A spacesuit provides almost none. Everything is thin. You are currently sitting at the bottom of an ocean of air roughly 60 miles deep. That ocean keeps your fluids liquid, blocks radiation, moderates temperature, delivers oxygen. Remove it, and you have about 90 seconds. In 1960, U.S. Air Force pilot Joseph Kittinger ascended to over 100,000 feet during Project Excelsior and jumped. A glove seal failed. His hand swelled to about twice normal size. After landing and repressurization, it returned to normal within hours. Human skin is gas-tight and resilient, but only for brief exposure. In 1971, the crew of Soyuz 11, Georgy Dobrovolsky, Viktor Patsayev, and Vladislav Volkov, perished when a ventilation valve opened prematurely at about 200 miles altitude. The cabin depressurized over roughly 30 seconds. They were not wearing pressure suits. 30 seconds. Autopsies revealed ebulism. Afterward, Soyuz crews wore pressure suits during launch and re-entry. The capsule carried 2 instead of 3. Lessons in physics are sometimes paid for in lives. The laws governing boiling water on your stove are the same laws governing survival in space. Pressure keeps liquids liquid. Insulation slows heat transfer. Radiation follows predictable rules. Nature does not negotiate. If the bladder has a hole, gas escapes. You cannot persuade a vacuum. The next time you scratch your hand and barely notice, remember the invisible ocean pressing down on you, about 14.7 pounds per square inch, roughly 100 pounds over your hand. You don't feel it because internal pressure balances it. Remove that balance instantly, and equilibrium vanishes. Space travel is not safe because the environment is forgiving. It is possible because engineering builds a narrow bridge across unforgiving physics. 13 layers between boiling from the inside and returning home. If you were floating outside the station, Earth rotating beneath you, would you stare at the view or inspect your gloves? I know what I would do. I would check my gloves,